Mercury is the innermost planet of the solar system, and since the reclassification of Pluto, the smallest, a scorched, airless world of striking extremes that orbits closer to the Sun than anything else of its kind. Its radius is just under 2,450 kilometers, only about 38% of the Earth's, which makes Mercury smaller even than the giant moons Ganymede and Titan, though far denser than either. For most of the space age it was, among the least known of the planets, glimpsed only in fragments, half its surface never seen. Yet the little world nearest the Sun turns out to be one of the strangest, an iron planet with an outsized metallic heart, a magnetic field it has no business possessing, water ice hiding in the eternal shadows of its poles, and a way of turning on its axis that ties its day to its year. This chapter follows Mercury from its orbit inward to its core. Sitting so deep in the Sun's gravity well, Mercury moves faster than any other planet, sweeping around its orbit at some 47 kilometers a second, half again as fast as the Earth. That closeness comes at a price. The Sun's warmth here is fierce and Mercury's gravity is feeble. The pull at its surface is barely a third of the Earth's, and a rock flung upward at only 4¼ kilometers a second would escape into space altogether. Between the intense heating, which gives gas molecules the energy to flee, and that weak grip which cannot hold them, Mercury has never been able to keep a conventional atmosphere. What thin veil of gas it does possess is not an atmosphere in the ordinary sense at all, but a ghostly, ever-renewed exosphere so sparse that its atoms scarcely ever meet, a distinction we shall return to. For now, picture a bare world of rock, open to the full glare and blast of the Sun. The first great clue to Mercury's nature is its weight. For a small planet it is astonishingly dense, about 5½ times as dense as water, second among the planets only to the Earth. But the Earth's high density is largely a trick of its own gravity, which squeezes its interior into a smaller volume. Strip that compression away, and Mercury's underlying, uncompressed density comfortably exceeds the Earth's. The only way to make a rocky body so heavy for its size is to load it with metal. Mercury, the numbers insist, is fractionally far richer in iron than any other terrestrial planet. Its core alone accounts for something like 70% of its mass, against barely a third for the Earth, Venus or Mars. This single fact, an iron planet with only a thin rind of rock, is the central puzzle of Mercury, the thread that runs through every theory of how it came to be, and we shall follow it to the very end of the chapter. Mercury's path around the Sun is the most eccentric of all the planets, not a near circle like the Earth's, but a pronounced ellipse that carries it from 46 million kilometers out to nearly 70 million and back on every circuit, so that the Sun looms far larger in its sky at closest approach than at its most distant. Its orbit is also the most steeply tilted, leaning some 7 degrees to the plane in which the other planets travel. And yet, the planet's own axis stands almost perfectly upright. Its tilt is the smallest in the solar system, a mere fraction of a degree. That near-vertical spin has a remarkable consequence at the poles. Because the Sun never climbs more than a hair above the horizon there, the floors of certain polar craters lie in perpetual darkness, never once touched by a sunbeam in billions of years, permanent cold traps in which, on the hottest of planets, ice can somehow survive. How Mercury spins was, for a long time, simply guessed wrong. By analogy with the Moon, which keeps one face forever toward the Earth, astronomers assumed Mercury was locked the same way to the Sun, one hemisphere in eternal day, the other in eternal night. That belief stood for most of the 20th century, and it was mistaken. In 1965, 2 astronomers, Pettingill and Dice, bounced radar pulses off Mercury from the Great Dish at Arecibo and read the planet's rotation in the shift of the returning echoes. The answer was not a locked day but a spin of about 59 Earth days, and, tellingly, that period is exactly 2/3 of Mercury's year. Mercury turns 3 times on its axis for every 2 circuits of the Sun, a 3-to-2 spin-orbit resonance, a stable rhythm into which the tides had slowly coaxed it, made possible precisely by that very eccentric orbit. No other planet keeps time with the Sun in quite this way. The resonance makes for a very strange sky. Turn slowly 3 times while circling twice, and the interval from one sunrise to the next stretches to about 176 Earth days, a single Mercurian solar day lasting 2 full Mercurian years. Stranger still is what the Sun does near the planet's closest approach. There, for a few days, Mercury's headlong orbital motion briefly outpaces its steady spin, and to an observer on the surface the Sun appears to halt in the sky, reverse course, loop backward, and only then resume its normal march. a retrograde stutter found nowhere else among the planets. And because the eccentric orbit brings certain longitudes to face the Sun at that scorching closest approach, Mercury has hot poles and warm poles, fixed points of greater and lesser heat, baked into the same two spots on the surface, orbit after orbit. That thermal geography, we shall see, is written directly into the planet's rocks. With almost no air to move heat around, Mercury endures the most violent temperature swings of any planet. At the point directly beneath the Sun, near closest approach, the surface climbs to around 700 Kelvin, some 420 degrees Celsius, hot enough to melt tin and lead. Yet on the night side and in those permanently shadowed polar craters, the temperature plunges to about 100 Kelvin, close to minus 170 Celsius. Few places in the solar system hold such fire and such cold so close together on one small body. The slow rotation only deepens the contrast, giving each patch of ground long hours under the full weight of the Sun and long hours in the dark to shed its heat. This ferocious cycling cracks and fatigues the surface rock, drives volatile substances to creep toward the cold traps, and, as we shall see, helps to carve some of Mercury's most peculiar and most youthful landforms. Mercury also holds a special place in the history of physics, for its orbit would not quite behave. The long axis of its ellipse slowly swings around the Sun, and by the 19th century astronomers had accounted for nearly all of that motion, the tug of the other planets, the wobble of the Earth from which they watched, save for a stubborn residue of about 43 arcseconds per century that no known force could explain. Some proposed a hidden planet closer to the Sun than Mercury and even named it Vulcan. It was searched for and never found. The resolution came in 1915 when Einstein's new theory of gravity, general relativity, predicted an extra twist to Mercury's orbit of almost exactly 43 arcseconds a century, with nothing adjusted to make it fit. It was the first hard, quantitative triumph of the theory that reshaped our understanding of space and time, and Mercury, of all worlds, was the proving ground. Until recently, almost everything known of Mercury's face came from a single visitor, Mariner 10, which flew past 3 times in the mid-1970s and photographed a little under half the surface. The other half remained a blank until the MESSENGER orbiter arrived in 2011 and for the first time mapped the whole planet. What it revealed was no dead, featureless ball, but a world with a rich and complicated history. 3 great kinds of terrain emerged: the oldest, heavily cratered highlands, saturated with the scars of ancient impacts, broad, rolling into crater plains, older still in places and stretching across much of the globe, and younger, smoother plains where floods of lava had once welled up and drowned the older landscape. Mercury, it turned out, had been shaped not only by bombardment from without, but by fire and movement from within, a planet that had lived a geological life of its own. The grandest scar of all is the Caloris Basin, a crater some 1,500 kilometers across, one of the largest impact basins in the entire solar system, gouged out near the end of the Great Early Bombardment, close to 4 billion years ago. Its name means basin of heat, for it sits squarely on one of Mercury's hot poles, and MESSENGER found its vast floor flooded with volcanic plains and fringed by vents that once erupted both in flowing rivers of lava and in violent, explosive bursts. Directly opposite Caloris on the far side of the planet lies a jumbled expanse of hills and grooves, the so-called weird terrain, thought to have been shaken up when the shock of that colossal impact raced around the globe and converged on the far point. By long tradition, Mercury's craters bear the names of dead artists, writers and composers, Beethoven, Tolstoy, Rembrandt, so that the map of this sun-blasted world reads like a roll call of human culture. Mercury's most telling landforms, though, are not craters but cliffs. Snaking across its surface are long, curving scarps, some hundreds of kilometers in length and more than a kilometer high, where one great slab of crust has been thrust bodily up and over another. They are the signature of a planet that has been shrinking. As Mercury's iron interior slowly cooled over the ages, the whole body contracted, and its rigid outer shell, left with too much surface for a smaller sphere, buckled and broke in compression, throwing up these wrinkles and thrust cliffs. The total shrinkage amounts to several kilometers off the planet's radius. Most striking of all, some of these scarps look geologically fresh, cutting across tiny young craters that ought long since to have erased them, a hint that Mercury may be contracting still, quietly quaking to this day. Far from a frozen relic, it seems, the little planet is a world caught in the slow act of cooling. MESSENGER also turned up something entirely new. The hollows, shallow, rimless, flat-floored dimples, bright and fresh-looking, that cluster on crater walls and floors where a certain dark material is exposed. They seem to be forming now, as some volatile ingredient of the rock is slowly lost to space by the sun's heat and the sputtering of its wind, eating the surface away from within. Stranger still was the chemistry the spacecraft's spectrometers read out. Mercury's crust is deeply chemically reduced, almost starved of the iron oxide that darkens the moon, yet startlingly rich in sulfur, and richer in the moderately volatile elements potassium and chlorine than anyone had expected. And the dark tint of the whole planet, it emerged, comes not from iron but from carbon graphite, the remnant, most likely, of an ancient crust that floated to the surface like scum on Mercury's early ocean of molten rock. Every one of these findings would deepen the mystery of the planet's origin. Then there is the paradox of ice on the planet nearest the Sun. Because Mercury stands so upright, the floors of its polar craters never feel a single ray of sunlight, and there the cold is so unrelenting that water ice can lie frozen for billions of years. The first hint came in 1991, when radar beamed from the Earth caught bright, telltale echoes at both poles, the radar fingerprint of thick, clean ice rather than rock. MESSENGER clinched it from orbit 3 ways at once. Its instruments sensed abundant hydrogen buried at the poles, measured the coldest crater floors gleaming bright as ice should gleam, and confirmed that those bright patches lay exactly where sunlight can never reach. The buried store is large for so small a world, perhaps 1,000 billion tons of ice, delivered, along with a dark crust of carbon-rich organic matter, by the comets and volatile-rich asteroids that peppered the young inner solar system. Fire and ice, on the same scorched globe. What of Mercury's interior, that great iron heart the density demands? Its size was pinned down not by drilling but by watching the planet turn. MESSENGER measured with exquisite care how Mercury's spin axis tilts and how the planet rocks very slightly back and forth as it orbits, a gentle nodding called libration. The upright axis, held in a delicate balance as the orbit slowly wheels, betrays how the planet's mass is arranged, strongly concentrated toward the center in a large, dense core. And the size of the rocking reveals something more. It is too large for a wholly solid planet, which means Mercury's core is at least partly molten, its mantle free to sway because it is not rigidly bolted to the mass beneath. The core, these measurements show, reaches out to about 80% of the planet's radius, proportionally far larger than the Earth's, with, deep within it, a solid inner core slowly freezing at the very center, much as our own planet has. Among Mercury's greatest surprises was the 1 Mariner 10 found first, back in 1974, a global magnetic field. A small, slowly turning planet was not supposed to have one, for a magnetic field of this kind must be generated by a churning, electrically conducting liquid core, a dynamo, and Mercury seemed too small and too sluggish to sustain the necessary motion. Yet there it was, and MESSENGER later mapped it in detail. The field is a genuine oddity. It is extraordinarily feeble, at the surface only about 1% as strong as the Earth's, and it is lopsided, its magnetic equator shifted markedly to the north, so that the field is far stronger over the northern hemisphere than the southern. Explaining a field so weak and so off-center has become a leading problem in the theory of planetary dynamos, hinting at a molten core that is thin, perhaps layered, and stirring in ways we do not yet fully understand, but stirring, crucially, even now. Feeble as it is, that field is still enough to carve out a small bubble in the oncoming solar wind, a magnetosphere, a miniature and frantic cousin of the Earth's. So close to the Sun, and shielded so weakly, Mercury takes the full force of the solar gale, and its magnetic bubble is battered down to barely half a planetary radius above the surface. Under a strong enough blast it can be crushed right to the ground, letting the solar wind strike the bare rock directly. Everything about this magnetosphere runs fast. The great cycle by which the solar wind's magnetism links up with the planets, loads energy into the tail and unloads it in bursts, a process that takes about an hour at the Earth races through in a mere couple of minutes at Mercury. MESSENGER watched the boundary crackle with knots of twisted magnetic flux, sometimes 10 and more a minute, as the Sun and the little planet ceaselessly, violently, exchanged their fields. That relentless bombardment feeds the ghostly exosphere we set aside earlier, the thin skin of gas that stands in place of an atmosphere. It is no true atmosphere at all. It is so tenuous that its atoms almost never collide with one another, and it is continually torn away and continually replenished, its atoms knocked loose from the rock by sunlight, by the solar wind, and by the tiny hammer blows of micrometeoroids. Its makeup was first read from the Earth in 1985, when astronomers caught the bright yellow glow of sodium, the very same spectral lines that color a street lamp, shining from Mercury's tenuous veil, and found potassium the year after. Sunlight itself then pushes those liberated sodium atoms gently away from the sun, streaming them into a faint, comet-like tail that trails millions of kilometers behind the planet. In its glow, the exosphere becomes a kind of remote spectrometer, each element betraying, by the color of its light, the chemistry of the surface from which it was struck. Only 3 spacecraft have ever visited Mercury, for it is, against all intuition, one of the hardest places in the solar system to reach. A probe falling sunward toward Mercury gains enormous speed, and shedding enough of it to slip into orbit demands either a prohibitive load of fuel or a long, patient dance of gravity, assists repeated swings past the planets to bleed the excess away. Mariner 10 pioneered that trick in the 1970s. Messenger perfected it, looping past the Earth, Venus and Mercury itself again and again over 6.5 years before at last easing into orbit in 2011, where it worked until its fuel ran dry, and it was sent deliberately to its end on the surface in 2015. Its harvest was transforming. The global map, the offset field, the polar ice, the shrinking crust, the strange volatile-rich chemistry, the oversized core, nearly everything in this chapter, in one way or another, we owe to that one small, doomed, brilliantly navigated machine. Mercury's story is far from finished, for a new mission is already on its way. BepiColombo, a joint venture of the European and Japanese space agencies, launched in 2018 and is named for the Italian mathematician who first explained Mercury's 3-2 rhythm and worked out the very gravity-assist path that Mariner 10 would fly. It is threading its own long trajectory inward, 1 swing past the Earth, 2 past Venus and 6 past Mercury, to break gently into the inner solar system, and after a redesign forced by a fault in its propulsion, it is now due to settle into orbit late in 2026. Uniquely, it carries not 1 orbiter but 2, which will part company on arrival into separate paths, one low and close to map the surface and interior, the other wider, to study the magnetic field and the exosphere. Measuring the planet from 2 vantage points at once, they promise to settle the very questions, the dynamo, the core, the origin, that Messenger could only pose. So we return at the last to the great puzzle: why is Mercury so drenched in iron? For decades the favoured answers were violent ones. Perhaps a fully formed Mercury of ordinary rocky makeup was struck a colossal, glancing blow by another young world, a collision that blasted away most of its rocky mantle and left the dense iron core behind, or perhaps the fierce heat of the young sun simply boiled its outer rock away. Both ideas share a fatal difficulty, and it was Messenger that exposed it. Any process violent or hot enough to strip Mercury's mantle should also have driven off its more delicate, volatile elements. Yet Mercury's surface is generously stocked with exactly those elements, the sulfur and potassium and chlorine that such a scorching should have banished. An iron-rich planet ought by these theories to be volatile-poor. Mercury is volatile-rich, and so attention has swung toward gentler origins, a planet, perhaps simply built, from the very start out of unusually iron-laden, chemically reduced material at the innermost edge of the newborn solar system. All of Mercury's peculiarities in the end tell one story: the long, slow cooling of a small body with an enormous iron core. Its early fires of volcanism died away billions of years ago as the interior chilled. Its crust has been wrinkling and contracting ever since, and yet in its still molten outer core, enough motion survives to run a magnetic dynamo, and at its surface the hollows and the drifting exosphere show a world being reworked even today. Mercury is a planet caught in the act of freezing, not dead but slowly dying and letting us watch. And it has grown newly important beyond our own system, for astronomers are now finding dense, iron-heavy worlds around other stars, supermercuries, for which our own scorched, secretive neighbour is the nearest guide we have. The least explored of the planets is fast becoming one of the best understood, even as its central riddle. How a world so rich in iron came also to be so rich in the very substances that iron-making ought to destroy waits still for its answer.